Hey there, welcome to my channel. My name is Wojciech and I'm a computer science student who's passionate about computer graphics. In this series, we'll be exploring the world of procedural texturing. We'll start with the fundamentals and gradually we'll build our way up. In the first episode, we'll cover the basics of geometry, materials, and textures. And then we'll move on to cover the mathematical foundations in the next episode, where we'll cover various types of useful functions. As we progress through the series, we'll learn how to combine these functions to form interesting shapes and patterns. And we'll also explore techniques to transform these shapes to introduce even more complexity. We'll also delve into tiling 2D planes with patterns and introducing randomness to the use of noises, rather than focusing on a specific software or programming language. We'll dive deep into the mathematical concepts that empower procedural texturing. By building the tools ourselves, we'll have a deep understanding of the underlying concepts, giving us a solid foundation that we can take no matter where our artistic or technical journey might take us. So, if you're interested in learning about this powerful tool for creating stunning textures, then join me on this exciting journey to the world of procedural texturing. This episode is broken down into 7 sections, and it is best to watch them in order, since each one builds on the previous section. If you need more detailed timestamps, you can find them in the description below. So let's not waste any more time and let's jump right into the topic. Let's start by taking a moment to talk about one of the biggest challenges in computer graphics: how to create realistic images that accurately represent the world around us. To achieve this goal, we need to first understand how we describe the appearance of objects. Take a closer look at the permanent marker and the mechanical pencil. Although they both serve the same basic function, they look quite different from each other. But why is that? Well, one obvious factor is their geometric structure, which affects how they reflect light. However, there's more to it. Another key factor is that the marker is made of plastic, while the mechanical pencil is made of metal. This has significant impact on their visual appearance, as each material interacts with light in a different way. However, there's another aspect: the microscopic structure of our objects. The marker has a rough, matte surface, while the mechanical pencil has zones of varying roughness. While this microscopic structure is technically a part of an object's geometry, it is so small that it is almost always treated as a property of the material in computer graphics. It's common practice to use 2 different scales to describe the visual properties of virtual objects: the geometric scale and the material scale. Basically, if you can see the object's geometric structure from a normal viewing distance, then you would use geometry to describe it. On the other hand, if you can't see the object's geometric structure from a normal viewing distance, then you would use the material scale to describe it. But here's the thing: what counts as normal viewing distance depends on the scene. If you're filming a tree from far away, you might not be able to see the details of its trunk's geometry. So, you would describe its visual properties using the material scale. But if you move your camera closer, you might start to see the tree's geometrical complexity, in which case you would introduce the geometry scale to describe the visual properties. Throughout the series, we'll create both textures that affect the geometric and material scale, which is a standard approach in computer graphics. But first, let's take some time to study the geometry. There are many options available for representing geometric data, including constructed solid geometry and voxel geometry, among others. However, the most widely used method is polygonal geometry, which has gained its popularity for its discrete nature that makes it easier for computers to work with it in various scenarios. In polygonal modeling, the idea is to create a rough representation of 3D shapes by using many simple flat shapes, called polygons. While a few polygons are enough to describe some shapes, like cubes, it gets tricky when trying to model smooth and organic shapes. The more polygons used to represent a 3D shape, the better approximation can be. However, as the number of polygons increases, it requires more memory and computational power to render. While computer technology has advanced significantly, it still has some limitations. Therefore, when creating complex scenes, it is important to be strategic in using available resources. There are a few terms that you will need to know. The smallest element of polygonal model is called a vertex, which is essentially a point in space. These vertices are then connected to form edges, and those edges can be further connected to form polygons. In addition to these three fundamental elements, polygonal models often include normals, which are vectors that indicate the direction perpendicular to the polygonal surface. In the simplest scenario, there are normals that correspond to each vertex or polygon. Normals play a vital role in both geometry editing and rendering. Any alterations made to the normals can significantly impact the appearance of the object. Let's now shift our focus to the material scale. Photorealistic rendering relies on statistical models called BXDF functions to simulate the interactions between light and surfaces. While you don't need to understand the intricacies of these models, as a rendering engine user, you are presented with an abstraction of a BXDF function, known as physically based shader. The principal shader is a prime example of physically based shader, and we'll be using it throughout the series as a reference. The principal shader was introduced by Disney in 2012. It is widely used for its simplicity, and it is implemented in many popular rendering engines. The shader provides a set of controls that mimic the physical properties of real-world materials, and is designed to simplify the process of creating realistic materials. It takes into account properties such as diffuse color, roughness, or metallicness, among others. The diffuse color is an important aspect of material's appearance, and it is one of the key parameters in the principal shader. This color determines the overall hue of the material without any shading or highlights. The diffuse color is typically specified using three numbers between 0 and 1, which represent the amount of red, green, and blue color, of course in RGB values. Roughness is also a crucial parameter, as it characterizes the degree of microsurface roughness. When the values are high, the reflection becomes more scattered and the light bounces off in many different directions instead of just one. The value of roughness ranges from 0 to 1, with 0 representing a perfectly smooth, shining surface, and 1 representing a perfectly rough, matte surface. Metallic is a parameter that controls how much a material behaves like a metal. In principal shader, metallic is typically assigned a value between 0 and 1, where 0 represents a non-metallic material and 1 represents a fully metallic material. We've covered only a fraction of the properties of principal shader, but for now, let's move on. Take a moment and consider how you would go about creating a 3D model of the marker by combining various 3D models and assigning a single material to each one. When creating the specific model, one would need to create at least 3 materials and multiple 3D models that would be combined to form the final object. For instance, each printed letter on the marker would need a separate 3D model to be made and assigned the right ink color. But this approach is not only impractical and time-consuming, but it is also very inefficient. That's why computer scientists have come up with a technique called texturing to solve this problem. Texturing is a technique that makes it much easier and faster to create 3D objects with different properties in different places. This is useful because pretty much everything in the real world has areas that look different from each other, like a wooden table that has darker and lighter parts, or a brick wall with variations in color and texture. By using textures, we can quickly and easily create these variations without having to model each tiny detail individually. Texturing is a broad term covering many different techniques for spatially altering properties on 3D models. I'll start by showing you a simple example that illustrates the important aspects of texturing. Flip is a character living in a three-dimensional world made up of polygons. If we want to add colors to him, we can slice him up into small pieces and place them on a table with drawing on it. When we place a piece of Flip on it, the drawing gets imprinted on the piece. By slicing Flip carefully and drawing on the table with care, we can color him this way. Let's take a closer look at the mathematical principles that govern this process. When we think about Flip's surface, we imagine it living in three-dimensional space, which can be denoted by real numbers to the third power. Similarly, our drawing is in two-dimensional space, which can be represented by real numbers to the second power. And the colors of our drawing are represented by the closed interval from 0 to 1 to the third power. To connect these three different spaces, we need two functions. One function to map points from Flip to the two-dimensional plane, denoted as f, and another function to map points from the two-dimensional plane to the colors, denoted as g. The entire texturing process can then be described using function composition. We can think of f and g as two separate stages of the process, where f takes a point in three-dimensional space and maps it onto a point in the 2D plane, and g takes a point in the 2D plane and maps it onto a color. In this context, the function f that maps three-dimensional space to two-dimensional space is commonly referred to as the UV map. This naming convention is used because, in texturing, we often use axes u and v to describe two-dimensional space instead of the usual x and y used in mathematics. The function g, in this context of texturing, is commonly referred to as the texture map. Don't worry if the notation seems confusing at first. We'll explore these concepts further in the next episode, where we go deeper into the mathematics. The previous example we discussed is just one special case of texturing, but it is a very common one. To start, we can experiment by changing the range of the texture map. Given our understanding of principal shaders, let's apply this knowledge to texture maps. We've already learned how to create a texture map for diffuse color. Let's now try it with roughness. Here is an example where I applied a roughness map to a sphere. By assigning higher values to certain areas of the sphere, I was able to create a rougher appearance, while lower values resulted in smoother and more polished areas. This made the rougher parts of the sphere appear less reflective and more scattered, as their roughness values were closer to 1. On the other hand, the smoother parts had values closer to 0, which made them more reflective and less scattered. To better understand this, we can refer back to the texturing diagram and adjust the output of the texture map to correspond with the possible range of roughness values, which can be visualized as a line segment on the x-axis ranging from 0 to 1. Mathematically speaking, the range is now a closed interval from 0 to 1. Using texture maps to spatially alter materials is a powerful technique. But let's not forget our promise to explore how we can use them to change the geometry itself. Before we dive into that, here is a fun exercise for you to try. Take a look at the shader in your preferred rendering software and identify a few parameters that control the material's appearance. Then challenge yourself to create a texture map function in a mathematical sense that you would use to generate such a texture map. This exercise will help you to gain the confidence to create your own textures that modify any shader's properties. When it comes to altering geometry with textures, there are three major techniques that you should know: bump mapping, normal mapping, and displacement mapping. Let's start with the displacement mapping, which is perhaps the easiest one to understand. Ironically, it is also the hardest one to implement in rendering engine. Displacement maps are texture maps that provide render engine with instructions on how to add a geometric detail before the actual rendering process begins. We assign a value between 0 and 1 to each point on the surface of our object, which tells the render engine to move the point a certain amount in the normal direction. However, there is one stage before that, subdivision. Essentially, the render engine subdivides the geometry and then displaces it. The displaced, subdivided geometry is then known as displacement geometry. Note that the normals of the displacement geometry are different than those of the input geometry. In combination with the geometric structure, they create a new complexity. What if we didn't create the displacement geometry, but simply alter the normals as if we did displacement? That would be bump mapping. This is a simplification, but it is useful to imagine it that way. However, the disadvantage of changing just normals is that under some angles, the result might look fake. This is especially obvious when looking at the silhouettes of a bump map model. While bump mapping accepts essentially the same input as displacement mapping, it produces different results. Bump mapping is faster because it doesn't have to create the displacement geometry. Last but not least, there is normal mapping, essentially a more flexible version of bump mapping. Instead of letting the computer compute the normals for us according to a single variable input, we give the computer the normal vector itself. This way, we can achieve a wider variety of effects that are often better tailored for our task than a bump map. In conclusion, if speed is your top priority, you should go for bump or normal mapping. However, if you want the most accurate results and don't mind paying for the computational costs, then go for displacement mapping. Throughout the series, we'll be working mostly with displacement maps, since I'm more interested in creating great visual results than in performance. However, if you are interested in learning more about the mathematical theory behind normal maps, let me know in the comments below. It's worth noting that creating normal maps from scratch requires some knowledge of multivariable calculus. But don't worry, I'll be happy to break it down for you in a future video if there's enough interest. I highly encourage you to experiment with texture map ranges on your own. There is no limit to what you can create using a texture map. For example, you might even try creating a texture map that alters bending of light rays in interesting ways if you're developing your own rendering engine. The possibilities are endless, so use your imagination and have fun exploring. Let us dive into how altering the texture map domain can change our texture. Just a quick note, I'll be referring to texture map domain as texture space, which is a common term used in computer graphics. Although I have demonstrated a two-dimensional texture space as an example, it is essential to know that it is not the only option available. Creating a UV mapping function is a complex and time-consuming process that requires skill to execute well. A poorly designed UV map can result in visible artifacts. Fortunately, we can avoid such issues by using a different texture space. By changing the texture space to encompass the entire 3D space, in some cases, we can avoid the UV mapping process entirely. This is because our texture map lives in the same dimension as our model, although sometimes we might still need to use the function that maps our object to the texture space, even when they have the same dimension. In my opinion, 3D textures feel more natural than 2D textures. By the way, 3D textures are often called solid textures. They are particularly useful for capturing objects with complex internal structure, such as the wood grain in a piece of lumber. It can be really tough to show all the different variations of the grain in 2D texture space, and it can end up looking flat and fake. But with 3D texture space, it's way easier to create textures that look realistic. Texture maps have endless possibilities. Suppose you're rendering a lava flow and want to make the magma change color based on the temperature. In this case, you can introduce temperature as fourth variable of the texture map, making the texture vary not only with position, but also with temperature. The result would be a more visually striking and realistic lava flow, with hotter areas appearing brighter and more vibrant, while cooler areas appearing darker and less intense. Regarding input for texturing, the options are virtually limitless. It doesn't have to be restricted to 3D space as in our initial texturing example. Instead, any input you desire can be used. For example, you could use a 4-dimensional space as an input for texturing process. Although the specifics are beyond the scope of this discussion, the possibilities for altering the input are endless. To wrap it up, we'll focus on creating texture maps, especially diffuse color maps, roughness maps, and displacement maps. While there are other types of texture maps, mastering these three will provide you with a solid foundation for creating any other texture map that you might need. With solid understanding of the underlying techniques and principles, you'll be able to create a texture map that suits your specific needs with ease. Up until now, we've discussed only what texture maps are and how they are used. But how do we actually create them in practice? Let's dive into it and take a look. When it comes to making texture maps, there are two main approaches to choose from: procedural and non-procedural. Procedural texture maps use algorithms and math functions to create output values, while non-procedural textures rely more on pre-existing data. But it's not always black and white which approach is being used, since there can be overlap between the two. So let's take a closer look at each approach to get a better grasp on that. First, non-procedural texturing, which can also be called declarative texturing. I personally prefer the term declarative because it's more accurate than non-procedural. The reason is that almost everything you do on a computer involves a procedure of some sort. So the term non-procedural can be misleading when it comes to describing what's actually happening behind the scenes. Declarative texturing relies on pre-existing data stored in a specific data structure, such as bitmap image. It can represent various texture maps, such as diffuse, specular, or displacement maps. Bitmap images are a popular choice in declarative texturing, especially for 2D textures. To get a better understanding of how it works, let's take a peek under the hood. When you give a 3D software an image and place it onto the UV plane, the software processes the image using certain algorithms to avoid any artifacts, and then uses it as a lookup table. If we ask about a point with certain UV coordinates, the corresponding value of the edited image on the UV plane is returned. However, it's worth noting that this process is actually much more complex than what I have described, and we could spend hours discussing it in detail. Interestingly, declarative texture maps can also be used for solid textures. There's a generalization of bitmap images into 3 dimensions, known as voxel maps. The only issue is that the voxel maps require a significant amount of storage. For example, a 2D 8-bit image with 3 channels and resolution of 2024 by 2024 pixels only takes about 3 megabytes of storage, while a voxel image with the same data and resolution of 2024 to the third power takes up over 3 gigabytes, which is over 1,000 times as much. As we increase the resolution, requirements grow cubically, making the use of declarative textures for solid textures problematic. Although 3 gigabytes may not seem like a huge amount, with the high-end machines available today having hundreds of gigabytes of operating memory, it might sound not so bad. However, the reality is a bit more complicated. I've created graphs to illustrate the required memory to store image in different dimensions, and the result might surprise you, because they're in different units. While the storage requirements for 2D image with a given resolution are around 200 megabytes, which isn't so bad, in 3 dimensions, you'll need a whopping 1,500 gigabytes. Loading that into memory is borderline impossible. And if you thought that was crazy, try to imagine storing 12,000 terabytes in operating memory. It's just insane. Luckily for us, procedural texturing allows us to create texture maps with higher dimensional texture spaces without involving any additional costs. So let's now shift our focus to the procedural approach to texturing. Defining what exactly procedural texturing is can be a bit tricky. As I've mentioned before, almost everything we do on computer involves a procedure of some sort. However, I found a nice general description of procedural techniques in this book. Procedural techniques are code segments or algorithms that specify some characteristic of a computer-generated model or effect. For example, a procedural texture for a marble surface does not use a scanned-in image to define the color values. Instead, it uses algorithms and mathematical functions to determine the color. Let me walk you through an example of mathematically defined procedural texture map. I'll call this function t with a subscript d, which represents the word displacement. The function takes in two-dimensional coordinates as an input, which means the texture space is also two-dimensional. The output of the function is a value between 0 and 1. If you're unsure why the function yields such a result, don't worry. In upcoming episodes, I'll delve into how to generate such functions. One of the greatest advantages of the procedural approach is the ability to parameterize our procedural functions. Instead of creating just one texture map, we can generate an entire class of them simultaneously. This means that the user of the procedure can select a specific texture they want to use from the available options. To illustrate this, let me take the first example a bit further by introducing a parameter denoted by p. By varying p in the relatively simple mathematical function, we can obtain different results. Take a look at all the different textures we can generate just by changing a single variable in the function. This powerful phenomenon is known as database amplification, where a small amount of input data can generate a large amounts of output data. It's crucial to understand that there are two types of procedures, implicit and explicit procedures. While sometimes they can describe the same textures, they are useful in different scenarios. The key difference between them lies in the way they are executed. Let's analyze our previous example for this. In the previous example, we saw how a procedural texture can be implicit, meaning that we ask for its value at a certain point, and it returns us the value at that point. However, we can also create explicit procedural texture that generates the same result. Instead of answering queries about specific points of the texture, we could use the procedural function to generate a bitmap image that we can then use in the texturing process. This approach is still considered procedure because the texture is generated based on a procedure, but the procedure is now explicit. Throughout the series, we'll primarily focus on implicit procedures, since they are usually more useful in texturing. However, it's worth noting that explicit procedures might be better suited for certain tasks, or we might not even have an implicit procedure available to generate a specific result. Let's take a moment and compare the procedural and declarative approaches. However, it's important to know that the advantages described in this section are only potential advantages, as incorrect implementation might result in some of these advantages being lost. Procedural texturing can give you a lot of creative freedom by allowing you to create patterns that seem to go on forever and fit together seamlessly. This means that you can create procedural textures to cover large areas, like a vast landscape or the surface of an entire planet, and it will look natural. On the other hand, declarative texturing has some limitations due to the storage restrictions. If you try to tile an infinite plane using declarative textures, you might end up with noticeable repetition in the texture. This can make it challenging to achieve the seamless look when working with large areas. Another great advantage of using procedural texturing is the ability to have virtually limitless resolution. Although, in fact, the resolution is limited by the numerical precision of your rendering software. For almost all practical purposes, it can be considered limitless. On the other hand, the resolution of declarative texturing is limited by how it was created in the first place. Procedural textures are usually stored in computer's memory as machine instructions, which are executed when you request a specific texture value. On the other hand, declarative textures require you to load the entire data structure into the computer's memory, which requires way more memory. When working with solid textures, the difference is especially noticeable due to the storage scaling issue I mentioned earlier. The problem affects both the long-term storage of textures and the working memory of the computer. However, since long-term storage is now relatively inexpensive, the main challenge is the amount of working memory required. One drawback of procedural textures is their impact on rendering times, as they are evaluated on demand. In contrast, declarative textures can be looked up almost instantly. Therefore, the more complex the procedural texture, the longer time it takes to render the final output. This leads us to the difficulty of creating procedural textures. When creating declarative textures, you simply use your camera and your favorite 2D editing software such as Photoshop, which is quite easy. Then you plug in the texture into your favorite 3D software. And it is almost guaranteed to be fast depending on the type of texture maps that you're using. Creating procedural textures can be more challenging than creating declarative textures, because it requires a good understanding of math and algorithms, as well as careful consideration of how to implement them for optimal performance. If you don't implement the functions efficiently, it can negatively impact the procedural's performance, making it slower to render. One of the main advantages of procedural texturing is that it allows you for quick editing by just changing the parameters. In contrast with declarative texturing, you need to manipulate your image with 2D editing software like Photoshop, or even go back and capture a new image. This advantage of procedural texturing can save you a lot of time and effort. However, it is important to note that the procedural textures can be edited quickly only as long as the desired changes are parameterized. If we needed to change something else, we would have to change the procedure, which can be real time consuming. On the other hand, with declarative textures, we have quite a high level of control to what we can edit, as long as we know how to manipulate the image. Even adjusting the smallest details is possible with declarative textures, and it almost always requires less time than editing the procedure. I hope you enjoyed the episode as much as I enjoyed creating it. From the basics of computer graphics to the intricacies of texturing, we've covered a lot of ground today. I hope that you found it informative and entertaining. In the next episode, we'll dive deep into the math behind procedural texturing. I know that it might sound a bit daunting, but I promise to make it as easy as possible to understand. And hey, if you have any questions or suggestions for topics I might cover, don't hesitate to let me know. Before I go, I want to mention that I have a Patreon account where you can support me and help me continue creating content like this. I'm still working on figuring out some benefits for my supporters, but I promise to have something in place before the next episode. It takes a lot of time and effort to put these episodes together, and your support means the world to me. Thanks again for tuning in.